Assalamu alaikum. Welcome students. In the last lab session, we performed analysis for the mechanical system with 1 degree of freedom. Now we will extend our analysis to a mechanical system having 2 degree of freedom. The system considered for this sake is here. I'm redrawing it. Uh, Here spring mass M1, damper M2 and spring. This is K1, this is K2, displacement X1, sorry, XA and displacement XB, and the friction between mass M1 and surface is B1, and friction between mass M2 and surface is B2. Now here we are applying force on mass M1, which represents node XA. As we have discussed how we can develop equivalent network which help us in writing a mathematical equation at nodes in theory of this course. So I am writing equation of motion at both nodes XA and XB directly. So equation of motion at node XA is F is equals to M1 d square XA. This d represents derivative operator plus B1 dxa plus K1 XA plus B3 dxa minus XB. This is equation number 1. Now we will write equation of motion at node XB. So the second equation will be B3 dxa minus XB is equals to M2 d square XB plus B2 dxB plus K2 XB. So these are the two equation of motions at both nodes. Now we will convert these two equation into 4-state equation. So now assuming state variables one is x1 is equals to xa, second is x2 is equals to dxa, third is xb, and fourth is dxb. Now putting these values in equation 1 and 2. So first state equation will be f is equals to m1 d x2 plus b1 x2 plus k1 x1 plus b3 x2 minus x4. I am rewriting this equation, so x2 dot, this will, I am writing this as x2 dot, which is derivative of x2 with respect to time, is equals to f minus k1 x1 minus b1 plus b3 x2 plus b3 x4 over m1. So this is first state equation. Now second state equation, I can write the second state equation by putting this substitution in this equation. So second state equation will be x1 dot is equals to x2. I can write third state equation by putting the substitution in this equation. equation number 2. So writing third state equation, b3 x2 minus x4 is equals to m2 dx4 plus b2 x4 plus k2 x3, or I am rearranging to write x4 dot, which is x4 dot is equals to b3 x2 minus k2 x3 minus b2 plus b3 into x4 whole upon m2. So this is the third state equation, and I can write the fourth state equation by putting this equation in this. So x3 dot is equals to x4. So this is the fourth state equation. Now solving these four state equation using Matlab by assuming suitable values for m, b and k. So I have already written the Matlab script for this sake. So here is the function I have defined as it is necessary in ODE 45 to write equations in the form of function as discussed in the previous lab session. I have named the function as multiple node system. You can use any name of your choice. Input is t and x and output is dx dt. This is the function keyword represents we are writing a function. I have assumed m1 b1 k1 and m2 b2 k2 b3 and f as this. So these are the assumptions. Now here we have to write four state equation. So I have created a matrix with 4 rows and 1 column having zeros. So the first state equation is x1 dot is equals to x2. This is the, I am assuming this as first state equation. x1 dot is equals to x2. So dx dt1 is equals to x2. Second state equation is here. I have assumed this as second state equation, which is x2 dot or dx2 over dt. So dx2 over dt is equals to this one, f minus k1 into x1 minus b1 plus b3 into x2 plus b3 into x4 whole divided by m1. Third state equation is here. I have assumed this as third state equation, which is dx3 by dt. So dx3 by dt is equals to x4. Now the fourth state equation is x4 dot, which is equals to this much. So dx dt4 is equals to b3x2 minus k2x3 minus b2 plus b3 into x4 whole divided by m2. Now in this function definition we have written all the four state equation. Now writing another script to use this function in evaluating x1, x2, x3 and x4. So ODE 45, name of the function, second argument is the timestamp, which is we are finding the value of this x from timestamps 0 to 400 seconds, and this vector represents the initial condition. It means x1 initially x1 is 0, x2 is 0, x3 is 0, and similarly x4 is also 0. This figure represents a new figure. So subplot 2, 1, here we are creating two areas in a single figure, and I am using first area plot t, x1 we have comprehensively discussed in the previous lab session why we have written x1 like this in plotting, and x label is time, y label is displacement, as x1 is displacement in our case. X1, the assumed state variable, is the displacement at node A. So, and the title is displacement at node A. Second is plot t comma x2, which is time and velocity. Velocity at node A here. X2 is dxa over dt, which is velocity. Similarly, this is the new figure, and in this new figure we also have created two areas to be plotted. So plot t comma x3 grid, and x3 is again displacement, but it is the displacement at node xb. So here x3 is equals to xb, which is the displacement at node xb, and the second area for this figure is t comma x4, which is the velocity at node b. So now let's run this script. So these are the four plots. This is displacement at node A, and this represents velocity at node A. Similarly, this figure, this graph represents displacement at node B, and this graph represents velocity at node B. Now here you can see velocity. After some time, the value of velocity is 0, as expected, since we have applied force on this system and we are moving this system forward. So after some time, the forces will get balanced due to this spring and this spring. So velocity of both these masses will be 0. Also you can observe this that the displacement of node A, which is displacement of mass m1, is 20 after some time, but the displacement of mass m2 is 0, as this system will come to the same position, as we are applying force at this mass, but we are not applying the force at mass m2. So this will move forward and backward, but it will again after some time it will move to its initial position. But for this m1, as we have constantly applied this force, so although the velocity will be 0 after some time, but displacement, it will be held at some constant displacement, which is in our case 20 for the assumed values. Now this was all about lab session 3. You can make a similar observation in this case also, uh, as we did in lab session 2. I will make a formal assignment for this also in Google Classroom. Also, you have to conclude what you observed by looking at all these plots. Now moving towards next lab session 4. In this lab session, we have to model electrical system using state space representation, and then we have to analyze the state equation by solving those equations using Matlab script, as we did in previous lab sessions 2 and 3. The electrical system considered for this sake is drawn here. I am redrawing it. voltage across resistor is VR, voltage across inductor is VL, and voltage across capacitor is VC. Current flowing in all of these elements is I. So now writing a mathematical equation for this system by applying KVL in this loop. So E is equals to VR plus VL plus VC, or I can write E is equals to I into R, current flowing in the resistor multiplied by R, plus LDI plus VC. This will become equation number 1. Assuming state variables, we have studied in theory lectures about how to choose state variables for electrical network. So state variables are x1 is equals to Vc and x2 is equals to I. So putting these substitutions in equation 1, E is equals to x2R plus LD x2 plus x1, or I can write dx2, which is x2 dot, to be equals to E minus x1 minus x2R over L. So this is first state equation, and I can write the second state equation as, we know voltage across capacitor is integration 1 over D is integration of I with respect to time. So moving this D to this side of equation, so it will become dVc is equals to 1 over Ci, or Vc is a state variable x1, so dVc will become x1 dot, so x1 dot is equals to 1 over Ci. This is second state equation. Now writing a Matlab script to solve these state equation. Here I have created a function just like we created in previous lab session. I named this function as RLC. Input is time and x, and output of this function is dx dt. The assumed values for R, L, C and the applied voltage are here. Now since we have two state equations, so I have created a matrix of 2 rows and 1 column. First state equation is, I considered it as first state equation. So x1 dot is 1 over Ci. So dx dt 1 is equals to 1 over C multiplied by x2. Similarly, second state equation x2 dot is this much. So here I have written like this: dx dt 2 is equals to E minus x1 minus R into x2 whole divided by the inductance, which is L. Now in this script I have called this our function RLC in the ODE 45 function, which is the syntax of this function. I have plotted the response from 0 to 500 seconds, and initially both the state variables and x1 and x2 are 0. Now here we have plotted these two state variable. First state variable is x1, which is Vc, as we have considered here. X1 is Vc, and second state variable is the inductor current, or we can say the loop current, as same current is flowing through all the elements. So first state variable x1 is capacitor voltage, and the second state variable x2 is the inductor current. So let's run this script. Now here you can see the voltage across capacitor starts from 0, and it then comes to the final value, which is the 60 volt as applied to the network. And inductor current starts from 6 amps and then it decreases down to 0 amps. This behavior of the network can be predicted physically, as initially the charge on the capacitor is 0, which gives us 0 volt at the terminal of capacitor. The charge in the capacitor starts to increase with time, as evident from the figure. And at 60 volts, the capacitor cannot charge more, as we have applied 60 volts to the network here. We can we can charge capacitor more by increasing the applied voltage. The current flow will be 0 after capacitor is charged, as evident from the plot of current, which starts from 6 amperes when the capacitor was fully discharged and decreased down to 0 when the capacitor is fully charged. This was all about lab session 4. There is a lab exercise at the end of lab session 4. Here you have to write a state equation for this system. You know how to do it. Then use Matlab script to solve these state equations, and then you have to explain the resulting plots in your own words. For example, you will observe the inductor L1 inductor current will start from some constant value and then decrease down to some another constant value, depending upon the values of R1, L1, L2, R2 and C selected. But L2 inductor current will start from 0 and increase up to a constant value. You will also observe the inductor L1 and L2 current will become same after some time. You have to explain all these points in your own words. I will also make a lab assignment for it in Google Classroom formally. That's it. Let's end our today's session here. We will continue from here in the next session. Allah Hafiz.